Hello everyone, in this video I will explain you how to solve an inverse kinematics problem of a robotic system in MATLAB. The example that we will consider is given over here. This figure shows a robotic system with 2 degrees of freedom. The degrees of freedom are theta 1 and theta 2. The goal is to compute the angles theta 1 and theta 2 if we are given the coordinates of the tool center point C. Before I start, I have to mention the following. It took me a significant amount of time to create this video and other videos. So if you like the videos I make, please consider subscribing or hit the like button. Thank you very much. By using basic trigonometric identities and rules, it is possible to relate the coordinates x and y to the angles theta 1 and theta 2. The equation will look like this. If you want to know more on how to derive these two equations, you can watch my previous video and you can read the tutorial that I made that's given over here. In this particular tutorial, I explained how to derive these two equations and how to solve them analytically for theta 2 and theta 1. In the interest of brevity of this video, I will not explain this procedure. If you want to refresh your knowledge or if you want to learn how to derive analytical solutions to inverse kinematics problem, please watch the previous video and read this lecture. Links will be provided in the description below. So let us go back to our original problem. So having these two equations that relate x and y with the angles theta 1 and theta 2, I want to solve these two equations. For this specific case, we can solve it analytically, and this is explained in the previous video. However, for more complex cases and for robotic systems which has more complex configurations and more degrees of freedom, it is challenging to solve these equations analytically. Consequently, we have to solve the equations numerically. In this video, I will use MATLAB to solve these two equations. However, you can generalize this procedure and you can write your own code in Python or C in order to solve these two equations for theta 1 and theta 2. The first step in solving this system of nonlinear equations for theta 1 and theta 2 is to write it in the so-called canonical form. The canonical form is given by the equation 2. So you take all the terms on the right hand side and you write them on the left hand side with the corresponding minus signs. And on the right hand side you will leave zeros. Once we have the system in this form, we can easily translate these two equations to MATLAB. So let's see how to do that. Okay, so the first step is to write a function that will give the left-hand side of the equation. This function will take theta as an argument. This will be a vector. The first entry will be theta 1. The second entry will be theta 2. Then we need to provide additional arguments, and these arguments are x, y, lengths of the segments L1 and the length of the segment L2. So for the given theta, given x, y, L1 and L2, this function will return the value of the left-hand side. This will be a vector. For example, the first entry can be 0.1, the second entry can be 0.2. If the equations are correctly solved, that is, if we know theta 1 and theta 2 accurately, the left-hand side is 0. Now, what you need to do, you need to save this function in a specific file. So you can save this function, you click on Save As, and you can create a folder. In my case, it's a temporary folder, and I will save this function over here. I will override because I wrote this script before. The next very important step is to add this folder to the MATLAB path. So you click here on add with subfolders, and you need to add the specific folder to your MATLAB path. This is important since we will call this function from another MATLAB script. Next, we explain the driver code for solving the system of nonlinear equations. But before we start, I have to mention one very important fact. First of all, notice how our system is written in MATLAB. We have basically defined a vector function that gives us the value of our left-hand side of our system. So if the solution θ1 and θ2 are correct, then the vector f will have very small values. So the first entry will be very small and the second entry will be also very small. Now, behind the hub, MATLAB is solving the system of nonlinear equations by formulating and solving an optimization problem that has a form that's very similar to the form that I will explain over here. So we have our vector function f, and this vector function has the entries f1 and f2. These f1s and f2s are basically the equations in this system. So f1 will be the left-hand side over here in the first equation, and f2 will be left-hand side over here, the second equation. Now, MATLAB aims at actually solving this optimization problem. Minimize with respect to θ, where θ is a vector consisting of θ1 and θ2, this objective function. So this objective function is Euclidean 2 norm that's being squared. It should look somehow like this. So basically, if we expand this cost function, we will obtain something like this: f1 squared plus f2 squared. Now, you might ask me the following question: why does this work? Well, if the solution is correct, that is, if θ1 and θ2 are close to solutions, f1 will be close to 0 and f2 will be close to 0. So basically, if the solutions are correct, our function, our objective function, will be close to 0. So we're trying to minimize this objective function. By minimizing the objective function, we are actually ensuring that θ1 and θ2 are close to the exact solutions. So this is what is happening behind the scene. MATLAB will try to solve an optimization problem. Here I have to mention that there might be slight variation on this theme, right? So maybe the solution not exactly formulated like this, but in a very similar manner. Okay, so let us go back to our MATLAB code, and now we can better understand what's happening behind the hub. So since we'll be calling some optimization algorithms, we need to specify first the parameters of these optimization algorithms. So we can use the function optimoptions, optimization options. We specified the function that we'll be calling. We are calling the fsolve. Fsolve is a function for solving a system of nonlinear equations. We specify the algorithm that's going to be trust region method. We specify display option that we want to display iterations. We want to count how many iterations we need until convergence. Then we use the parallel approach, right? We can use the parallel approach or not using the parallel approach to speed up computations. Here, because the system is very small, I will use false option for the parallel argument, that is, I'm not going to use a parallel solver. Then you need to specify the optimality tolerance, and you need to specify the function tolerance. Without specifying even these parameters, MATLAB will basically call some default solver. Okay, now that we have clarified that, in order to measure the accuracy and the performance of our solution process, we need to define some test cases. So here I actually defined 2, or better to say 3 test cases for testing the accuracy of our algorithm. Here I'm specifying where is my 2C TCP in the Cartesian coordinates. So I'm specifying 0.4 in the x, 0.4 in y directions. Here I'm specifying the link lengths, right? I'm specifying the link lengths. And let us see how this whole procedure, how these test cases will look physically, from the physical point of view. Okay, so this is the test case 1, the one that I currently explain. Here, these are the x and y coordinates, 0.4 and 0.4, so this is 0.4 in x, 0.4 in the y direction. And now from basic graph, we can see that basically the true solution should be theta 1 is equal to 0 and theta 2 is equal to 90 degrees. So we expect that our procedure will give us theta 1 0, theta 2 is 90 if we specify this position. Okay, so in order to basically run our algorithm, we need to specify the initial guess for the solution. And here you should really keep in mind that your initial guess for theta 1 and theta 2 has to be relatively close to physical configuration. Where do you expect that your end effector will be, and how the robot will be positioned? What is the configuration over here? Okay, so here I expect, for example, a small value for theta 1, and I expect, let's say, a larger value for theta 2. So I will use 30 degrees for theta 1 guess and 60 degrees for theta 2 guess. Now, since this is initial guess in degrees, let's run this. Let's see. So here's my initial guess, 30 and 60. I need to transform everything to radians. So this will be my initial guess in radians. Again, you should keep in mind that cosinus function takes radians as arguments, right? Although there is a MATLAB function called cosinus d, cos d, that takes degrees as arguments. However, this particular function, cosinus, takes radians as arguments. So I need to transform my solution in order actually the initial guess to radians. And over here, I will call the function fsolve. I will provide as an argument my kinematics, the function where I defined my system of nonlinear equations. I need to specify the argument here, that this means at theta, means that the solution will be evaluated at theta. And to this kinematics function, I need to specify theta. This will be my basically solution, right? That will be iterated. This will be x, y, x and y coordinates that I specified previously, and the lengths of the joints, or actually lengths of the segments. Then I need to specify initial guess in radians, and it's very important to link these options to the function, to the fsolve function. Okay, let us run the solution and let's see what happens. Okay, so here's our diagnostics. We have 5 iterations. We have how many function counts? 15 function counts. And here's our objective function. Here's our function f. Actually, that's defined as Euclidean squared norm of our function f. Here's the norm of the step. Norm of the step is basically the Euclidean norm of the optimization step, and here's our optimality. We can see that the equation is solved, the relatively stringent, under stringent tolerances, and here's our solutions in radians. Now, before we convert the solution from radians to degrees, it's interesting to analyze the solution. So let us evaluate our solutions in radians, and let's see the value of our function f. We expect that for basically the solution, the value of the function f will be small. So by calling the kinematics, specifying the solution in radians, x and y coordinates, L1 and L2, we should just get the value of f, since this function returns f. And we can see that f1 is small and f2 is small, so the solution should be okay. Let us convert the solutions to degrees, and voila, here's our solution. Theta 1 is 0, theta 2 is 90 degrees. So we're able actually to find the true solution. This is the test case 1. In my previous video tutorial, I explained that the solution of the inverse kinematics problem is not unique. And to test that, we will analyze the second test case, right? In the second test case, the TCP will be at the same position as in the first case. However, the robot configuration will look differently. From physical point of view, we can reach this point either in this way, or we can reach it from this side, right? That's why the inverse kinematics problem or its solution are not unique. And I explained this in my previous video. So how are we going to test this scenario? Well, to find the solution in this case, we'll just change the initial guess. Here, instead of using 30 and 60, we will use a different initial guess. So we'll say that basically theta 1 is around 70 degrees, and theta 2 is minus 70 degrees. Okay, so by setting the initial guess, we can actually retrieve different solutions of the inverse kinematics problem. But you need to know what is actually happening behind the scenes. Okay, so let us run the procedure again from the scratch and let's see what happens. We expect that the solution again will be 90 degrees and minus 90 degrees. So let's see the performance. Here it is. We are able to accurately solve or accurately compute the solution of the inverse kinematics problem for the second test case. Theta 1 90, theta 2 minus 90 degrees. Very good. Okay, and let us perform the third test, where we will set basically our robot to be in this position. So C will touch the x-axis, and the exact solution should be theta 1 is 0 and theta 2 is 0. So let us define this test case. Here you can just uncomment this line. Okay, so I will set the initial guess in degrees 10 and 10. However, here you also need to specify the correct position in the Cartesian coordinates. I'll assume that x is at 0.8, y is at 0, the length of the first segment is 0.3, and the length of the second segment is 0.5. So I'm defining basically the position of my TCP over here, and I'm defining an initial guess for my solution. It's 10, 10, but let's make the problem more difficult for MATLAB. Let's choose 30, 30, and let's see what happens. Again, here's our solution. Again, you can notice here that we need more more iterations to converge since the solution is relatively far from the exact solution. Okay, and let's see what do we get. Okay, we're getting minus 0.22 degrees for theta 1 and 0.4 degrees approximately for theta 2. Okay, very good. We are able to solve even this problem. Okay, that would be all for today. I hope that you like this video. If you like the videos I make, please subscribe or support my channel. Thank you very much and have a nice day.